All right, let's dive in. Ever get the feeling that chemistry is just for super smart scientists in white lab coats? Well, I'm here to tell you that's not true at all. Chemistry is actually the story of, well, everything. The world around us, the phone in your hand, even the air you're breathing, it's all just a series of amazing chemical recipes. So let's start reading them.
You've all seen this, right? Rust. It seems kind of slow, maybe even a little boring. But what you're really looking at is a secret transformation. It's a slow-motion chemical story where iron is turning into something completely new, right there in the open.
And then you've got the complete opposite end of the spectrum. This is respiration. It's happening inside your body right this second. It's the lightning-fast chemical reaction that turns your lunch into the energy you're using to watch this. So you've got slow decay and you've got instant energy. These transformations are absolutely everywhere.
So that's the big question, isn't it? How do we actually write down the story of what's happening? How do we explain iron becoming rust or a cookie becoming energy? Well, that's the language we're about to learn.
To write that story, we've got to understand the language first. So let's start by decoding the chemistry that's hiding all around us. And you're going to see it's a language that anyone can pick up.
So here's the bottom line. A chemical reaction is all about change, a real transformation. It's when the tiny bonds holding atoms together get broken apart and then they get rearranged to form totally new stuff with brand new properties.
And honestly, the best way to think about all this, it's like a recipe. A chemical equation is literally the recipe for every single thing happening in the universe.
And this is a really important difference. Think about a physical change, like ice melting. It's temporary, right? You can just freeze it again. You still have water. But a chemical change, that's permanent. When you burn a piece of wood, you're left with ash and smoke. There's no way you can unburn it. That's a chemical reaction.
And this is our recipe in action. On the left, you've got your reactants. Those are your ingredients. That arrow in the middle, that's the verb, the mixing, the baking, the cooking. And on the right, you get your products. That's the finished dish. Simple as that.
Okay, but there's one golden rule in this cosmic kitchen. You can't just make ingredients appear out of thin air. Whatever you put in has to come out. And this leads us to the great balancing act.
This is the fundamental law of the universe, really. It just means if you start your recipe with, say, 10 atoms of carbon, you have to have 10 atoms of carbon in your final dish. They might be attached to different things, but they all have to be there. It's like cosmic bookkeeping. Every single atom must be accounted for.
So let's walk through one. We've got magnesium and oxygen making magnesium oxide. First step, we write it out. Then we count the atoms. Okay, see the problem? We've got 2 oxygens on the left, but only 1 on the right. Not balanced. To fix it, we put a big 2 in front of the magnesium oxide on the right. Now our oxygens match, but wait, now we have 2 magnesiums on the right. No worries. We just pop a 2 in front of the magnesium on the left. Let's do a final check. 2 magnesiums on each side, 2 oxygens on each side. Perfect, it's balanced.
So now that we've got the basic rules down, let's check out the menu. There are a few common types of recipes, or reactions, that you'll see all the time.
First up, the combination reaction. This one's super straightforward. You take 2 or more ingredients, like carbon and oxygen, you put them together, and you get one single new thing, in this case, carbon dioxide.
Next is the total opposite, decomposition. Here, you start with one big, complex thing, and it breaks apart into smaller, simpler products. It's like a fancy dish deconstructing back into its basic ingredients.
Then things get interesting with displacement reactions. This is like a chemical dance-off. You've got a more reactive element, like iron, that comes along and just cuts in, kicking the less reactive copper out of its partnership. The iron gets the new partner, and copper is left all by itself.
And finally, we have a really important one, redox reactions. Think of this as a give and take. One substance gains oxygen, we call that oxidation, while another one loses oxygen, we call that reduction. The key thing is they always happen together. This 1-2 punch is behind everything from batteries to breathing.
Okay, so we've learned the language and we've seen the main types of stories. Now let's bring it all back to the real world and see how you can use this to read what's happening all around you.
Remember that rust from the beginning? Well, now we have the exact language to describe it. It's not just some vague change. You can now look at it and know exactly what it is, a slow oxidation reaction, where iron is grabbing onto oxygen from the air. You just decoded it.
Now what about the very energy you're using to listen to my voice and think about all this? Well, that's coming from what we call an exothermic reaction, one that releases energy. It's called respiration. That sugar from your food is reacting with the oxygen you breathe, and that equation on the screen, that exact recipe, is what is powering your brain and your body this very second. How cool is that?
So you see, chemistry isn't some far-off subject stuck in a textbook. It's the instruction manual for literally everything, written in a language of reactions and equations. And you've just learned the basics. You can now read the universe's recipes. So the only question left is, what will you go out and discover next?